This video will explain the basic use of real-world CAD slide routine. The slide routine got its name because it slides 2 or 3D pipe fittings, duct fittings, or other entities along an imaginary axis until it aligns with the selected alignment plane. We'll see how to use this basic concept to solve some routine but sometimes frustrating problems encountered while repositioning and aligning 2 and 3D objects. After some theoretical discussions, we'll move on to some practical applications. We'll slide the T and an elbow on the supply manifold of this boiler skid. We'll also slide the diffuser in order to align its vent with the inlet of the expansion tank above. We'll install the chill water supply and return piping shown here on this chiller. Then we'll connect the waste riser to the lav header above. We'll use the slide routine and a 3D rotation command to set the elevation and rotation angle of the Y. Let's start by covering some basic concepts. Since this video is basic, we'll be using the slide routine on piping runs that are flat or level, plumb or vertical, or return the pipe or duct run to flat or vertical. Graded pipe or angled pipe runs will be covered in separate videos. In light of this exclusion, we need to see what's meant by flat or level, plumb or vertical, or sloped or graded pipe. It's not necessary to memorize these definitions since the slide routine will automatically detect the orientation of the slide axis. However, if you're new to CAD, it will be helpful to understand the basic concept. In the field, a pipe or duct run that is level is commonly referred to as a flat run. In 3D CAD, a flat run is very similar. It is a run that is parallel with the world coordinate system as shown here as a red dashed line. A vertical pipe or duct run is commonly referred to as a riser or a pipe that is plumb. This is shown here as a blue dashed line. In 3D CAD, a riser is a pipe or duct run that is perpendicular to the world coordinate system's XY plane, which also means that it is parallel to the Z-axis of the world coordinate system. A slope pipe run is interchangeably referred to as a graded pipe run. A slope pipe run, shown here highlighted in green, is a pipe run whose axis is graded plus or minus 2.6% to the world coordinate system's XY plane, but not a 0% slope. This type of pipe run is usually found in plumbing systems and requires special consideration. When the slide routine calculates the axis of the pipe or fitting is sloped, it will offer several additional fitting alignment options. These options, as well as graded pipe's special requirements, will be covered in detail in separate videos. An angled pipe or duct run is a run that is not plumb, level, or sloped. A few examples of these types of runs will be covered in this video. To demonstrate the slide routine, we'll start with this basic set of fittings and pipe shown here. Let's switch to an elevation view to get a clear view of what the slide routine does. I've already set the PD mode variable to 35 to make the fittings and nodes more visible for this demonstration. Let's temporarily remove the Y and the L for clarity, and start the demonstration with the T. We'll be using the slide routine to slide the T along the axis of its barrel to align its branch and focal point with the blue pipe as shown here. Let's put the T back to its original position and use the slide routine to slide it into position. Before we start, we need to know what a slide axis is. The slide axis is an imaginary line the fitting will slide along, represented here by the red dashed line. The slide axis will always be defined by the first 2 points picked. In this case, the first point can be either end of the barrel of the T. The second point must be the fitting's focal point. The focal point is the point where the center line of the barrel and the center line of the branch intersect as shown here. All pipe fittings and most duct fittings installed with Mech-Q software will have a point or node placed at the fitting's focal point when the fitting is initially installed. Let's select the T. First, we are prompted for the first point on the slide axis. This point can be any snappable point along the slide axis regardless of the direction the T will eventually slide. In this case, we'll pick the end on the left. Now we are prompted for the second point, which in the case of pipe or duct fittings must be the fitting's focal point, which is represented by this node. Next, we are prompted for the branch end of the fitting, so we'll pick the center of the branch's end. Finally, we are prompted for the point to align with. In this case, we'll pick the center of the blue pipe. The T will slide along the slide axis until its branch aligns with the blue pipe represented by the blue dashed line. Next, we'll slide the elbow. You'll notice that the elbow, like the T, will be aligned with the point to align with at the same angle as the fitting's branch angle. In this case, it's 90 degrees. Simply put, For graded pipe, the slide routine will slide nearly any object or objects along an axis defined by the first 2 points picked and align it with the 4th point picked using the angle formed by the slide axis and the branch end. Let's slide the Y. The point selection is the same as the T and the elbow. We just need to make sure that the 2nd point picked is a focal point and the 3rd point is the center of the branch end. The slide routine will always slide the fitting to align the branch end with the alignment point using the branch angle, regardless of which end of the fitting's barrel is picked first. This feature is very handy, since depending on the viewing angle, it's not always apparent which direction the fitting will slide. Let's move the Y a few more times to illustrate this point. Currently the Y is aligned with the blue pipe. Let's align it with the red pipe. You can see that even if we pick opposite ends of the fitting, the slide routine will slide it to the proper alignment. Now let's align it with the yellow pipe. It doesn't matter which end we pick first as long as the focal point is the 2nd point and the branch end is 3rd. Let's see how the slide routine works using a real-world situation. Here we have our boiler skid project. First we'll remove the boiler itself to get a better view of the finished manifold we'll be building. We'll be using the slide routine to aid in building the pump supply manifold highlighted in magenta. The fittings whose position we'll be adjusting are the T and the elbow that are now being highlighted in magenta. Here we can see the skid before the manifold pipe and most of the fittings were installed. The weld neck flanges on each end of the manifold have already been installed along with the elbow and the diffuser. I have also pre-installed the T will be sliding on the weld neck flange. The slide axis for the T will be an imaginary line between the 2 weld neck flanges shown by the animated red dashed line. We want to align the branch with the elbow on the diffuser highlighted in magenta. The process to slide the T is the same we saw in the previous theoretical examples. We simply select the T, then pick the first point along the sliding axis. The first point could be any point along the axis, the center of the face of the elbow, the center of the weld neck flange, either end of the elbow's barrel, or any of the same points on the opposite side of the skid. This time we'll use the focal point of the L at the right of the screen. The next point picked is and must be the focal point of the T. The 3rd point we'll pick will be the center of the end of the T's branch. Finally we'll need to pick the point to align with. This point could be the center of the diffuser tank, the center of the weld neck flange, or the face of the elbow, since their centers all fall along an imaginary alignment plane represented by this gray screen. This means that even if the fitting to align with is not yet installed, picking any point that falls in this imaginary plane will cause the fitting to slide to the proper position. For the point to align with, we'll pick the center of the elbow's face. Now the T will slide along its axis and the branch will align perfectly with the elbow. Before we move on to the elbow, we should be aware that any time a 90-degree fitting on a level or vertical axis is slid, the rotation angle of the branch will have no effect on the final position of the fitting. This will not be true for non-90-degree fittings. We'll see why later in this video. For now, let's zoom in on the T. We can see that even if the branch of the T is rotated as seen here, the branch will still align with the alignment plane. This can be very useful in cases such as swing offsets where the rotation angle of the fitting cannot be established until the fittings are slid into position. I have zoomed out and pre-installed an elbow on the T and looked it up to eventually connect to the elbow on the diffuser, which is looking down. Let's use the slide command to slide the new elbow on the manifold to align it with the elbow on the diffuser. First we'll select the elbow to slide. We'll use the center of the face of the elbow to define the first point on the slide axis. Next we'll pick the focal point of the elbow for the other end of the slide axis. Now we'll pick the face of the elbow that will align with the elbow that's installed on the diffuser. Finally we'll pick the node on the face of the diffuser's elbow that we want to align the elbow with, and the elbow slides into position. To complete the manifold, all we need to do is install the pipe and the weldolet, and the manifold is ready for tagging and dimensioning. All this was done without drawing center lines or making calculations of any kind. The slide command only requires 4 point picks to slide an object into position regardless of the object's orientation in 3D space. In this next example, we'll look at the chiller manifolds in our central plant project. Let's remove the walls and doors for clarity. In this demonstration, we'll be placing the fittings and pipe on the chill water return riser highlighted here in yellow, and the chill water supply riser also highlighted in yellow. First, let's remove the chill water return riser pipe and fittings and the chill water supply pipe and fittings and move the valves back to their original position. We'll leave a portion of the manifold piping in place and use them for alignment points later. I've switched to an elevation view and reinstalled the second elbow on the chiller and looked its face up. Let's slide it to align with the butterfly valve above that it will eventually be connected to. For any 3D object such as this elbow, all we need to do is pick 3 points to define it. As we saw earlier, the first point can be anywhere on the slide axis, but the second point must be the focal point. For the third point, we'll pick the remaining face of the elbow. For the point to align with, we can pick any point on the center of the associated butterfly valve. Now we see the elbow slides into position. I've switched to a 2 viewport configuration with an elevation view on the left and an isometric view on the right. Let's use the slide routine to adjust the elevation of the elbow highlighted in yellow. We want its branch to be at the same elevation as the manifold it will eventually connect with, shown highlighted in yellow. First, we'll pick the point on the slide axis. Then we'll pick the focal point, and then the remaining face of the elbow. For the point to align with, we'll pick the center of the manifold. Now the elbow slides into position. I have switched to a single viewport for illustrative purposes. We can see that even though the elbow is not rotated towards a manifold pipe, it still ends up at the correct elevation. Anytime the slide axis is vertical and a 90-degree fitting is used, its branch will always be parallel to the World Coordinate System's XY plane or the level plane. This is similar to the T we saw earlier on the boiler skid manifold. I've switched to a dual viewport configuration with a plan view on the left and an isometric view on the right. Let's move the final elbow that's in the horizontal plane to align with the manifold it will eventually be connected to. The object selection and points we'll be picking are identical to all the previous examples. Make sure that the focal point is picked when prompted for. All of the fittings in this video were slid into position using the slide routine exclusively. In fact, the slide routine will almost completely eliminate the use of any type of centerline tool, temporary construction lines, or dimensional calculators. I've switched back to a single viewport to get a better look at the front view of the chiller. We need to change the elevation of the butterfly valves and the weld neck flanges. We want both valves to be at the same elevation, and we also want the top weld neck flange of the valves to attach directly to the elbow above. We could use the slide routine to change the elevation of the valves by picking the 2 points along the axis of the valves and picking the quadrant of the weld neck flange for the alignment point. However, that would leave the face of the weld neck flange at the same elevation as the face of the elbow with no room for a weld gap. Let's use the Type Z routine to change the elevation of the valves instead. The Type Z routine is covered in detail in a separate video. To use it in this instance, all we need to do is select the valves and their associated flanges. When prompted to pick the point for elevation alignment, we'll pick the top face of the weld neck flange. When prompted to pick for a point to align objects with, we'll pick the lower face of the elbow. We'll want to leave a 3/32 inch weld gap between the elbow and the flange, so we'll type -3/32 on the command line. The valves will move up to an elevation that will accommodate the weld gap. Since the valves are at the correct elevation, we'll press Enter twice to exit the routine. Now all we need to do is install the pipe and the chill water supply manifold is complete. I've switched to a front view of the chiller and removed all of the chill water supply and returns pipe and fittings except these 2 elbows. We can see that the 45-degree elbow needs to be aligned with the associated valve. In this case, the slide axis falls along this 45-degree line composed of the end of the fitting and the focal point. The alignment plane is an imaginary plane that is made up of the center lines of the valves and the weld neck flanges. What we have here is a common but unique fitting combination. Here the slide axis is at a 45-degree angle to the World Coordinate System, which is technically an angled slide axis. Angled slide axes are covered in a separate video. However, since the center line of the focal point and the branch end are precisely vertical or plumb, it will be treated differently than any other angled slide axis situation. Let's slide the fitting into position and see what happens. The point selection is the same as with the 90-degree elbows, being sure that the second point picked is the focal point. We'll pick the center of the weld neck flange above for the point to align with. Now the fitting slides into position. If we zoom in on the command line, we can see that the slide routine has given us some useful information. We see that the slide axis is sloped at 100% grade or on a 45-degree angle, and that the branch is vertical. Anytime the slide axis's angle to the world coordinate system causes the branch center line to be vertical, the slide axis will slide the fitting into position without any other options being offered. All that remains is to install and adjust the remaining pipe and elbows, and this portion of the chiller piping is complete and ready for spooling. Using the power of 3D CAD, all of this was accomplished without any construction lines or a single calculation. Now let's look at a pair of non-90-degree fittings and see what effect fitting rotation has on the slide routine and proper fitting placement. Here we see a typical lav header hookup. Let's remove the slab, perimeter beams, and joist to see what we'll be doing. We'll be connecting the 8th bin, shown here highlighted in yellow, with the Y also shown here highlighted in yellow. If we switch to a plan view, we can see that the elbow and the Y are not rotated properly for connection. Let's see what happens if we use the slide routine to change the elevation of the Y without rotating the fittings correctly first. I switch to a dual viewport configuration with an elevation view on the left and an isometric view on the right. We'll pick the points on the Y as normal and pick the end of the elbow for the point to align with. If we look at the elevation view, it looks like the Y is in the proper position. However, if we tried to connect them with a pipe, the pipe would be nearly horizontal since the riser and the header are not aligned with each other. At this time, the elevation of the focal point of the Y is 10 foot 11 and 3/16. Let's see what it is when we rotate the fittings before we use the slide routine. First, let's move the Y back to its original position on the riser and change the left viewport to a plan view. This time we'll rotate the fittings before using the slide routine. In the case of non-90-degree fittings, on flat or vertical runs, with like-angled fittings as we have here, we can rotate the fittings in any sequence, but must never use the branch as the target for the rotation angle unless that fitting is at its final rotation angle and elevation. We can use the focal point of the elbow or the Y as the point to align with for either fitting because the X and Y elements of the respective fitting's focal points will not change regardless of their rotation angle. This is true of any fitting whose axis is parallel with the world coordinate system's Z-axis. To rotate the elbow, we can select any point on its vertical axis for the two ends of the rotation axis. In this case, we'll use the center of the sleeve and the center of the coupling to define the rotation axis's center line. Now we'll pick the branch of the elbow for the handle point. We can use any point on the riser for the point to align with. The center of the sleeve, coupling, or pipe would work in this case because their centers are all parallel to the world coordinate system's Z-axis. Now we can see the 3D rotation routine has automatically rotated the elbow to the correct angle. This is because in this case there is only one rotation angle that will allow the elbow's projected center line to intersect the center of the riser. This is obvious when we look at the plan view on the left. Now let's rotate the Y. Even though it's above the elbow, it too will rotate to the correct alignment angle. Since the elbow is at its final elevation and rotation angle, we can pick its branch or any point along its vertical axis for the alignment point. In this case, let's pick the point where it connects to the coupling. Now let's slide the Y into position and connect it to the elbow with a pipe and couplings. Remember to use the focal point of the Y when prompted by the slide routine for the focal point. If we check the elevation of the Y's focal point, it's 10 foot 2 1/4 inches absolute compared with the elevation of 10 foot 11 and 3/16 as previously shown. The length of the connection pipe is 9 3/16 of an inch now compared with almost 0 inches as shown at the beginning of this example. Now that we have completed this lav connection, we see that there is only one additional step for using the slide routine for non-90-degree fittings on flat or vertical runs. The first step is to rotate the fittings to the proper angle. The second step is to use the slide routine to slide the fitting into the proper position. That's all there is to it. Now the fittings align properly and we have a perfect joint. Once again, the slide routine has used the power of 3D CAD to allow us to make this connection without calculations or troublesome 3D construction lines. But most importantly, it eliminated the need for expensive field cutting and fitting of the connecting pipe. Let's move back to the boiler skid project for the last demonstration of the slide routine. Here we can see the connection of the diffuser to the expansion tank. Let's remove the tank mount for clarity. When the diffuser was first installed, it was centered under the expansion tank's port and connected using a straight pipe as shown here. However, we needed to add a swing offset to compensate for tank movement, vibration, and manufacturing tolerances. Let's remove the connecting pipe and install the elbows and standard pipe nipples for the swing joint. What we want to do is slide the diffuser under the union above. Without the slide routine, we would have to either create temporary construction lines, then move the tank and erase the temporary construction lines, move the tank to the face of the elbow, then change the elevation of the tank so it sits on the skid's floor, or use the move command with point filters. However, with the slide tool, all we have to do is pick the correct points to define the half coupling that is welded to the top of the diffuser tank. Let's zoom in to get a better look at what we'll be doing. When prompted for the first point on the slide axis, we'll pick the lower quadrant of the half coupling. When prompted for the focal point, we'll pick the lower center of the half coupling. These 2 points will form the slide axis as illustrated in the elevation view. When prompted for the branch end, we'll pick the top center of the half coupling. These 3 points will define the coupling and appear to the slide routine as though we picked the points on a T or an elbow. Finally, we'll pick the center of the nipple above for the point to align with. Now the diffuser slides into position. All that's left to do is to install the last nipple and the connection is complete. Real-World CAD Slide Routine is a robust 3D CAD tool that was developed primarily for the mechanical detailing industry. This tool will nearly eliminate the need for construction lines, point filters, or the multiple use of the move command to reposition 2 or 3D objects. Additional instructional videos will show the versatility of the slide routine when used on sloped or graded pipe runs. Real-world examples in these videos will include lav and toilet headers, associated rolling offsets, and the use of the slide routine to avoid collisions with other 3D entities such as structural members and ducting. The slide routine was developed by Real-World CAD as a robust tool for the mechanical detailing industry. At Real-World CAD, we believe you shouldn't need a degree in software engineering to produce CAD drawings that are accurate, legible, and completed on time. That's good for you, good for your client, and good for the bottom line. The slide tool is available only in the Mech-Q software suite and AviCAD, which is now available from cadavenue.com.